Now we're going to bring together what we've seen in the last several series of videos. We're going to sketch graphs of functions using more detail than probably you've done in pre-calculus. We're going to include critical numbers, intervals of concavity, inflection points, and asymptotes as appropriate. Our first function is y equals -2 plus 3x squared minus x cubed. Before we do that, let's remind ourselves what we can see from the function and its various derivatives. From the function itself, I'll just call it f, we can get the domain. We can get the range. I don't always pay attention to that when I'm starting out, but it's true. We can get intercepts, x-intercept, y-intercept, asymptotes, points on the curve itself, and symmetry if you care about even versus odd and that sort of thing, if that applies. That's it for the function itself. And I mean, like this one here is a polynomial, right? So you kind of have an idea of what the general overall graph might look like. F prime is going to give me critical numbers by setting a derivative equal to 0, intervals of increasing and decreasing, and locations of extrema. And when I say locations of extrema, I mean x values. The y values come from the function, right? That's where we get the points. That does it for f prime. For f double prime, we can get intervals of concavity and locations of inflection points. And again, when I say locations of inflection points, I mean x values. So let's get to work on this function here, which I'll rewrite. And since it's a polynomial, we know that the domain is all real numbers. This is an odd degree polynomial, so we know the range is also all real numbers. For x-intercepts, I need to know where this function is equal to 0, and for that, I'm going to set the expression equal to 0. I'm going to multiply through by a -1, so the lead coefficient is positive. And because of the nature of this equation, x cubed minus 3x squared plus 2, this is a cube, so I don't get to factor it. I'm going to use synthetic division. And my spidey sense tells me that if I put 1 into, if I divide by x minus 1 essentially, then I'm going to get something nice here. So my coefficients are 1, -3, 0, and 2. Don't forget the linear term, which you don't see here. And then I'm going to drop 1 down and then multiply and add several times and end up with x minus 1 times the quantity x squared minus 2x minus 2 is equal to 0. So that tells me that x is equal to 1, and then if you use the quadratic formula, you will see that x is equal to 1 plus or minus the square root of 3. So our x-intercepts are 1, 0, and 1 plus or minus the square root of 3. We can see from the expression that defines the function that the y-intercept, that the y-intercept is 0, -2. And that's what I'm going to get out of the function for now. Let's move on to its derivative. Y prime is equal to, I'll put it in descending order, -3x squared plus 6x. And in order to find critical numbers, I'm going to factor out, say, 3x. That's going to leave me with x minus 2. And so my critical numbers are 0 and 2. Using these, I can find intervals of increasing and decreasing. So setting up a number line with 0 and 2 on the number line, we can see if I pick a number to the left of 0, that y prime is going to be negative, and so the function is decreasing on the interval from -infinity to 0. Between 0 and 2, the function, the derivative is positive, and so the function is increasing. And then to the right of 2, you can see we're going to get a negative value, which means the function is decreasing, and so the slope is negative there. Don't always assume it's going to alternate in sign, negative, positive, negative, because if the function has like a wiggle, you could go positive, 0 derivative, and then positive again. Just make sure that you actually take the steps and do the work. And I'm going to move on. That's what we're going to get from y prime for now. Y double prime is equal to -6x plus 6. And if I factor out a -6, I'm going to get x minus 1. And so I'm going to set up a number line here, and I'm going to put x equals 1 on this number line in between x equals 0 and 2 on the other number line, just for visual effect here. And if I pick a number to the left of 1, I can see that I'm going to have a positive value for y double prime, which means we're concave up. That looks like that. And then if I use a number to the right of 1, I'm going to have a negative value for y. Oh, I should label these y double prime and y prime. My gosh. That means we're concave down on the interval from 1 to infinity. That looks like that. And now the reason that I laid these out visually the way I did was because I wanted to emphasize the second derivative test. Looking where x is 2, that's in an interval where the graph is concave down. And so I can see that we have a local maximum at x equals 2. Likewise, I can see that x equals 0 is in an interval that's concave up. And so we have a local minimum at x equals 0. Also, because concavity switches from up to down when x is 1, we have an inflection point at 1 comma, and we'll figure that out and say now. For actual points on the graph, I'm going to go to an XY table here. The points of interest that we have are our critical numbers, 0, 2, and the point at which we have an inflection point, 1. So our values over here are going to be 0, 1, and 2. And yeah, here's y. And we already know that at 0, when x is 0, y is -2. When x is 1, y is 0. Those happen to be the intercepts that we found. And then if my math is correct, then putting 2 in place of x for the function is going to give me a value of 2. Therefore, I can say that the inflection point is at 1, 0. I can also say here that the local, pointed at the wrong number there, minimum is -2, and the local maximum is 2. We're going to draw a graph, but first I'm going to summarize everything that we've just found. I wanted to put it all on one screen in front of us here. So for the function y equals -2 plus 3x squared minus x cubed, we know the domain is all real numbers. The x-intercepts are 1, 0, approximately 2.730, and approximately -0.730. I did that instead of like 1 plus or minus square root of 3 because I'm actually putting these on a graph and I want to know where to plot the points. Y-intercept 0, -2. That kind of does it for y. Y prime, the first derivative, is equal to -3x squared plus 6x. From that, we got our critical numbers were 0 and 2. Intervals of increasing and decreasing. The function is increasing on the interval from 0 to 2 and decreasing from -infinity to 0, union to 0, or excuse me, to infinity. Notice parentheses at the for the intervals of increasing and decreasing, always parentheses, never brackets. Local minimum at x equals 0 is y equals -2. I wanted to be really clear that the at and the is are different things. The local minimum is the y value. Local maximum at x equals 2 is y equals 2. That does it for the first derivative. For the second derivative, we got y double prime equals -6x plus 6. The graph is concave up on the interval from -infinity to 1 and concave down on the interval from 1 to infinity. Again, parentheses on those intervals. The inflection point itself is 1, 0. Now let's put all this together in a graph. All right, we've got points that we can plot. Let's see, we've got the x-intercepts at 1, 0, at 2.730 approximately, and just ballparking it over there, and -0.730. In my head, I'm thinking like, oh, that's like -3/4. Y-intercept is 0, -2, and then we have a maximum value at 2, 2. And then we already have plotted 1, 0. And so we're going to draw this. So here I'm going to draw an interval that's concave up. And then I'm going to try and draw an interval that's concave down. And so that concavity should switch at 1, 0. To the right of the rightmost x-intercept, I'm going to draw a graph that goes straight down. I'm not going to wiggle it out like this because that would be concave up again, and I'm not allowed to have that, right? And, oh, I should mark numbers on my x-axis. I'm not going to mark all the numbers, just 1, 2, 3, 4. I'll just mark where like 5 is here, and then I'll say that this is 3 up here because that's as high as that thing goes. -3 down there, and then I'll just put like a -3 over there. Oh, fine. For over here, I'll just mark 3. I don't have to mark all of the numbers. I just need something to indicate what the scale is for the x and y axes. Now we got to finish this off. I got to be careful over here too. I don't want to accidentally bend this out like this so it's concave down, right? It's supposed to be concave up for the entire interval from -infinity to 1. And so I'm going to draw this concave. Okay, right here it goes concave down. I'm not really thrilled with that. So I'm going to fix that. And I didn't like that. I know it's kind of annoying watching me draw this. All right, I'm going to take one last shot at this. I'll come from up here. There, that should do it. And then you might wonder, well, how strict am I going to be on a test or something? Like, do we care if that's bends concave down like that? I'm not going to be that picky. I could be like, try me, but I'm not. What I don't want to see is something that bends out like this, or that is clearly got the wrong concavity, okay? Yeah, so give it your best shot, but this is how we put all the information together to draw the graph of a function.